May I have your attention, please? Okay, my name is Gaiman Yi. Welcome to the i4energy seminar. I'm the Technical Director of the i4energy Center. Also want to welcome those that are online viewing today's seminar. We have a treat today. We have Paul Wright, the Director of CITRIS. He's going to say a few words before we get started.
Well, I'd like to welcome everybody. I especially like to honor our good colleagues from Siemens who are in the building. If you could just put your hand up for a second, Thomas. And we have many other good friends. We have many other good friends today. As you probably realize, our work in demand response has been going for nearly 10 years now with the California Institute for Energy and the Environment. Carl Blumstein, the director, in the front here. And it was our great pleasure that 2 or 3 years ago we reached out to Professor Callaway in Michigan and recruited him to our program. And since then, he's really hit the ground running. He has a number of great projects going with our good friends at the lab. Thank you for coming today. And really, I leave it to Gaiman to make the major introduction, but it really warms my heart to think that not only is all this great group in the audience here interested in demand response and renewables, but we're now really beginning to hire a fabulous group of faculty, Duncan being the spearhead of that group, who will work on energy and efficiency and really make these big impacts in California that we need now. So thank you very much for coming today, and I'll just hand back to Gaiman to do the official introduction.
Thanks, Paul. And just before we get started, a reminder that everyone should put your compostable materials into the correct bins. As Paul mentioned, today's speaker is Duncan Callaway. Dr. Callaway is an assistant professor here at the Energy and Resources Group, which he joined in the fall of 2009. He also holds a courtesy appointment in the Department of Mechanical Engineering. Dr. Callaway's teaching focuses on power systems and energy efficiency. His research can be categorized into 3 areas: modeling and control of aggregated storage devices, power management, and system analysis of energy technologies and their impact. His work focuses on improving energy efficiency and renewable resource utilization through novel energy systems configuration and control strategies. Specific application areas include wind energy, demand response, load control, and plug-in electric vehicles. Prior to Berkeley, Dr. Callaway was a member of the research faculty of the Center for Sustainable Systems at the University of Michigan. He also worked in private industry in the Davis Energy Group and at Powerlight Corporation. After receiving his PhD in theoretical and applied mechanics from the Cornell University in 2001, Dr. Callaway held an NSF postdoctorate fellowship in the Department of Environmental Science and Policy at UC Davis. Let's welcome Duncan Callaway.
Great. Thanks, Gaiman. Okay. So is the mic okay? Does everybody hear me well? Okay, great. So it's really a pleasure to be here talking today. My objective will be to give a pretty high-level overview of some of the issues surrounding demand response and why I think it's well paired to the issue of renewables integration. But before I start, I really do want to very enthusiastically thank California Institute for Energy and Environment and the i4energy Center for supporting this work, and also my collaborators, Ashwin Kashyap, Dave Auslander, Roy Cifuentes, and Taylor Keep have put some really invaluable work into some of the things that I'll be talking about today. So just to give you a bit of an overview of what I'll be talking about. So I mentioned that I'm actually going to spend a fair bit of time just sort of framing the issues and talking about some of the decisions that we need to make if we're going to proceed with demand response for supporting renewables integration. So those will be the first 2 sections of the talk. I'll talk about some of the challenges to renewables integration and why we might want to pursue demand response to address those. And then I'm definitely going to talk about this first research effort that is supported by CIEE and i4energy, what I'm calling off-only approach to getting down and up regulation. So the idea is that we're going to try to switch loads off and use the natural dynamics of the system to try to get loads to actually increase their consumption at certain times as a result of letting them return to the grid. If there's time, I'm going to talk about this second project, probabilistic strategies for measuring and controlling aggregated loads. Okay, so first let's just go through some of these issues about challenges to renewables integration. I've got 2 or 3 slides that I've pulled from other industry studies and reports that I think really capture what the dominant issues are. So as most of you in the audience, or all of you I'd imagine, are aware that wind and solar comprising an increasing share of electricity generation, but the production is not only variable, electricity demand is variable, but production is also highly uncertain. And electricity demand is also uncertain, but renewables tend to be even more uncertain. And these are some events just last year that ERCOT, the Electricity Reliability Council of Texas, has published for what they thought wind was going to be doing over the span of 24 hours and what they actually got out. And I think one of the really staggering things to look at is the y-axis on these figures. We're talking about upwards of 8 gigawatts of production from wind farms in the state of Texas alone. But then we're looking at 2, 3 plus gigawatt deficits of or surpluses of production relative to what was expected. These are day-ahead forecasts, but it's interesting also to note, so everybody's worried about these things and looking at these issues. This is actually a study that was done by GE for New York, for the state of New York, and it's a little bit harder to see what's going on this figure, but what you want to look at is, so again, we've got power on the y-axis, time on the x-axis, and the green is what they actually got out for wind production. These are simulations that they did with about 3,300 gigawatts of, megawatts of wind in the New York footprint. And then you can see that there's a blue, what they simulated the day-ahead forecast would look like, but then also an hour-ahead forecast in red. And you can see that even at the hour-ahead level, and it's a little bit easier to see on this figure, there's pretty significant error that they still have to deal with, up to 500 megawatts or so in this particular case. This is over the month of January they were simulating. So the question then becomes, what are the consequences of this and how do we manage it? So at this point, if you think about what the consequences are, it's if you don't respond to those forecast errors, let's say that you plan to have something happen day ahead or hour ahead, and then you just sort of go according to your plan, well, then there's either a deficit or a surplus of power coming from the supply side. And at the very least, you're going to have large frequency excursions on the grid. But instead, what grid operators do is that they sort of charge they give a set of generation the task of standing ready to absorb that error. So it's basically like you do everything you can to plan, and then you've got a bunch of stuff that just sort of takes it as it comes. And so in particular, what happens is on sub-hourly timescales, in general, we have 5-minute energy markets that can move generation around relatively quickly to deal with whatever error or forecasting mistakes we make on the hour-ahead time scale. It's important that we have enough capacity online to not just handle big deviations, but very large ramps in production from wind or solar. And then if we go down to sub-5-minute forecasts errors, so of course these 5-minute markets are also working on a forecast of what's going to happen. Below 5 minutes, we use something called automatic generation control. The service is often called regulation, but this is basically like, you're no longer operating an energy market. You're just giving a system operator a dial where the system operator can just turn generation up and down as they need to. And so in this case, they procure a certain amount of capacity that is just sort of standing ready and available to do what they need. So thinking toward the future, California is really, I think, kind of a hotbed of massive projected growth in renewables. So we've got a 33% renewable portfolio standard target by 2020. And that would be 33% by energy, not by capacity. And there's a big difference when you think about the fact that wind and solar produce energy only for a fraction of the time that they're actually connected to the grid. Other states range from 5 to 40%. 40% is Maine, the state of Maine, and they're going to be operating in the ISO New England. So it's really the ISO New England's problem, and their total share wouldn't be 40%. So forecasting is certainly going to improve, but the error is inescapable. And if we think about what's happened, Pacific Gas and Electric and the California ISO have been trying to address what do they think they're going to need for balancing resources on the grid in 2020 if we meet this target of 33%? And they're saying that, in addition to everything we're going to build to meet load growth and everything that we're going to build to try to meet these renewable portfolio standards, we need 3 or more gigawatts of additional capacity on the grid just available to balance these forecast errors. So that's a really significant investment. And at this point, our best option is to look toward sort of fast ramping combustion turbines to do that job. So that sort of leads us to the question why and also how can demand response contribute to this challenge. So again, I'm going to start with an example of what happens in practice. So this is an event that some of you may have heard about. It was publicized pretty widely. In ERCOT, again, about 2.5 years ago, they had a forecasted wind to go, according to this blue line, over the span of, what are we looking at, about 6 hours. And what they actually got out was this yellow line here. So you can see that by the end of this period, they were looking at a deficit of about 1 gigawatt from what they had expected to have happen versus what they actually got out. And there was sort of a perfect storm that happened because at the same time, this is a really busy figure, but what I want you to pay attention to is the red line. So the red line is what electricity demand was doing on the same day. So ERCOT had, as wind, which is on this figure, was falling off faster than expected from the forecast, they also had demand going up much faster than they had forecast. This was their forecast, and what matters is that the rate is much faster than what they had expected. So what happened? They saw frequency decline to 59.85 hertz, which is a really significant deviation in large-scale power systems. So what they did was they called, in addition to bringing other generation online, what ERCOT did was they called 1.2 gigawatts of load that they had available to curtail. They had sort of established contracts with this load ahead of time. The way that they called them was literally calling them on the telephone. So they used the phrase verbal dispatch, or VDI, verbal dispatch instruction, which makes it sound, really fancy and special, but they're literally picking up the phone. But still, even though they were using this pretty crude technology, frequency was brought back in line in a matter of minutes. So this demand response event, even though we were using pretty crude approaches, had a really significant contribution to the performance of the system. Okay, so let's then think about sort of broadly. I'm going to spend the next few slides trying to sort of frame in broad terms what I think the benefits are to demand response and some of the challenges that we face to implementing it specifically for the purpose of renewables integration. So I think that arguably one of the biggest benefits is that there's a potential for a very fast response, essentially sort of emissions free, because we're not using we're not moving generation around, we're not having to build additional generation. We're taking things, and this is sort of addressed in the second bullet, we're taking things that are already connected to the grid and serving some other purpose, refrigeration, water heating, space conditioning. We have these loads on the grid for some other reason than to provide a service to the system. But if we can sort of bring them together to provide a service in addition to the power system, in addition to the service that they provide locally, then we've basically got like 2 value streams. And ostensibly, you don't have to pay as much for either one. They can sort of cover each other. So the second then big potential benefit, I think, to demand response is that you may not have to pay as much to get the service as you would if you were just building new generation, because this stuff we've already got loads on the grid and we just have to figure out how to coordinate it. Okay, but so then you might think, well, you're going to start moving loads around and you're going to, as a result, ask people to be uncomfortable or for their hot water to be cooler than they want it to be. But the beautiful thing about a lot of loads on the grid, it's about, in the US, it's about 50% of our electricity demand comprises loads that are thermal, and that they're ultimate service is to provide cool or heat. And the way that, or the beauty of these loads is that we basically charge them. If you think about a water heater, you operate a water heater for a certain period of time so that you bring its temperature up to where you want it, and then you stop until the temperature falls back down to some unacceptable level, and then you charge it again. So in that way, thermal loads are just like battery storage, whereas instead of thinking about moving a battery from putting power onto the grid or pulling power back off of the grid, in the case of thermal loads, we're just saying, well, we're going to operate around some average and reduce from that average or go up from that average. So you never obviously discharge a water heater. You can't put electricity back onto the grid. But just by moving away from where it would have been in the absence of control, you can get exactly the same benefit that you would get with a conventional storage device. And because water heaters, refrigerators, space conditioning, all of these things have what we call thermal capacitance. So temperature doesn't change instantaneously. If you start your air conditioner, it takes 10 minutes, 15 minutes for you to get to the point where you feel like you've got the temperature where you want it. And then you turn it off, and then the temperature floats again. So that means that we've got some slack, is what David Culler would call it, in terms of when these loads operate. So there's lots of flexibility because they have thermal capacitance. So let's see, what other points do I want to make? Yeah, depending on what kind of thermal capacitance, what we ultimately want is an amount of energy delivered over a time period. We don't care exactly how much power we're consuming at one instant in time. So provided that we deliver that energy over the right time scale, you're not compromising the end-use function of these loads. Then the other thing that I put in here just at the end that I think is interesting to consider is that, I'll talk about this a little bit more in a second, that ultimately we need to communicate with loads. We need to tell them, provide a service to the grid, and to do that, we need some sort of a communications network. And cellular networks are as good as anything else, or maybe not as good as a sort of fast broadband network, but we can get a lot of the information that we need over cellular networks, and these are globally available. So if you think about countries where energy infrastructure is relatively undeveloped, we could still try to deploy these kinds of strategies there to support variable production and uncertain production from renewables. Okay, so then on this slide, I'm just going to go through. These are questions that I'm not addressing today in entirety. I'm going to address maybe some of these questions, but I think that these are big picture questions that we need to worry about when we're thinking about demand response and renewables integration. So the first question is something that, that a number of people at Lawrence Berkeley Lab and at UC Berkeley are addressing, and that's what kind of infrastructure do we need? So we've got the thing that interfaces with the grid. We've got the load. But we don't necessarily have the thing that communicates to the load. And so, and we also don't necessarily have the thing that after receiving that communication signal actually causes the load to do something that you want it to. So we need communications and control infrastructure. There's an ongoing research project that David Auslander is leading, looking at a sort of uniform reference design for a gateway that would pull information in and then in an open referenced way disseminate information out to loads, or allow information to be disseminated to loads in a building. There's also the Open Automated Demand Response Project at Lawrence Berkeley Lab, which is doing terrific things in terms of creating an open standard for communications. One of the things that I think is interesting to think about, it's often dismissed, is advanced metering infrastructure, which some of you may be aware of. A lot of you probably have a smart meter now that PG&E has installed at your residence. And the big benefit of these things is that you can automate the reading of the data from these things. So PG&E doesn't have to send somebody to fight the dog at the gate to go read your meter. Instead, they just pull it up electronically. But one of the pitches that they made, that utilities make to public utility commissions to support the installation of these things, is that you can actually do two-way communication. So you can potentially disseminate information to these devices, to loads on the other side of the meter, and try to get service from those loads for power system purposes. But communication can be slow, unreliable, and so one of the things that I may have time to address today is the question of, in a communication-constrained environment, how do we get loads to do what we want them to, given that advanced metering infrastructure is a totally suboptimal from a communications bandwidth platform. But I should say that the advantage to it is that it's there already. So it's potentially a very low-cost thing. So another set of big picture questions is, okay, so let's say we can talk to loads. What do we actually tell them? What information do we give them? So one option is that we just give them a price. We say, this is the real-time price on the system. Do what you want with it. The alternative is that you say, you basically sign a contract with the owner of the load that gives you the option to control that load as you wish. And so you pay them some fixed amount, $10 a month on their electricity bill. And in response, you can do whatever you want with their load, subject to some constraint. You know, you say, well, I'm not going to let your temperature in your house, if it's an air conditioning control program, change by more than a couple degrees. And if you violate that constraint, then maybe there are penalties. I mean, the contracts aren't this sophisticated now, but they certainly could be in the future. So advantages to price, I think, is that it's sort of a transparent thing. There's less resistance, I think, to the idea of having, there's more resistance certainly to the idea of having somebody directly tell your loads what to do. You'd rather sort of conceptually say, well, just give me the price and I'll decide what to do. But I think that one of the disadvantages, especially for small loads, I'll talk about that in a second, is that, you know, I know at least personally, I probably don't have the attention span to go figure out exactly what is my demand curve for power, especially when all that I want eventually is an energy service over a long period of time, rather than some instantaneous amount of power that would be that the real-time price would reflect. So from a sort of headache perspective, I think that direct control, if the incentive is right, for the value of that option is right, then direct control can be better in certain situations. And then other sort of big picture questions, what kinds of loads should we target? One way of distinguishing them is that we could go for a few large loads. Let's say we want a gigawatt of capacity. Well, we could try to get 10 100 kW or if we want a megawatt of capacity, 10 100 kW loads, or we could go with 1,000 1 kW loads. So there are a lot of ways of thinking about what the trade-offs are here. Certainly with large loads, you can imagine that this question has a different answer, because if you just have a few loads, you can spend a lot more on your communications and control infrastructure. If you have if you have a lot of small loads, you don't have as much to spend on each one, assuming that ultimately the service that you're providing is the same. And if you know the industry at all, this is sort of like the ENERNOC model, and this is the ComVerge model. So these are two sort of major demand response organizations. And at this point, I would say it's probably fair to say that this model is winning, the few large loads. But I think that there are a lot of benefits to the lots of small loads idea, and this is one of the reasons. So this figure is taken from a Brendan Kirby paper where he's plotting, okay, so we've got probability that you have a certain amount of capacity available from a net amount of capacity, which is 600 megawatts. And then in the first case, we've got 600 megawatt generators, each one with 95% reliability. In the second case, we've got 1,200 500 kW responsive loads. So these are still actually pretty big loads. But we've got a lot more of them. And this is just by, for those of you that know probability theory, this is just by virtue of what the binomial distribution looks like and what happens when you start having n be really large. The variance on that distribution goes down. So the probability that you've got 500 megawatts of available responsiveness from these loads is essentially 100%, whereas you have less probability for these larger devices, even though the larger ones on their own have higher reliability. So this is one thing to think about. There are a lot of other issues, I think, to consider when we're talking about large versus small. And so I don't think that there's one silver bullet, but I will say today what I'm going to talk about with the research results is direct control of aggregated loads, and what I mean to imply by that is lots of small loads rather than a few large ones. And so I'll talk about trying to deal with communications constraints. It's more in the second project, which at this point I probably won't have time to get to, that I deal with this issue. And again, direct control small loads. And sort of the big picture guiding questions I think that we're trying to understand are how do we manage loads without impacting end-use performance? And I've talked about energy services over a period of time, so you can think of that question being rephrased if you were doing some sort of an optimal control problem. You've got a constraint on energy that you have to meet. And we're going to assume that if you meet that constraint, then you meet your end-use function objective. And then again, I've said this a few times, how do we do this in a communication constrained environment? Okay, so I'm going to talk about this first project, which I call load switch strategy for getting up and down regulation. Okay, so just for background, load switches are actually, maybe not widely, but they've been used for many decades actually for the purpose of peak demand reduction. The idea being that you interrupt the thermostat wire to an air conditioner, and you can basically cut the signal and turn an air conditioner off when peak demand is high. Load switches are getting more sophisticated, and that so actually this one, these are brand new products on the marketplace. This one communicates over Zigbee to an advanced metering device. This one here communicates over GSM, I think, cellular networks. But I think that suffice it to say that the fact that we've got new markets coming on, or new products coming onto the market, just right now for the purpose of peak demand reduction, suggests that these things, there's some interesting potential to them. I should also say that Joe Ito at the lab has done really innovative work looking at using these types of switches, or actually older, 30-plus-year-old switches, for spinning reserves. So basically doing what the ERCOT wind event did to try to get a bunch of demand off the grid very quickly, rather than just trying to do a long-scale, time-scale reduction in peak demand. But what we're asking in the research that I'll talk about today is, can we do even more than that? Can we do more than just curtail load over timescales that are of interest to renewables integration? And the reason I think that's an interesting question is because it may be a very cheap way to make existing appliances smart. So these load switches just basically sit on top of everything that's out there already. So we don't have to worry about putting new chips into a refrigerator or a water heater. This can sort of sit externally. But the key constraint then that we have is that all we can do is turn the loads off. We can't turn them on. And if we're thinking about this sort of storage analogy, we would like to be able to ask loads to consume a little bit more when the forecast error is such that there's a surplus of wind energy or solar energy. And so it's easy to imagine how you get them to consume less with these switches, but how do you actually get them to consume more? So that's what I'm going to try to sort of sketch out at a high level how these things work in this project. So what I'm going to do is basically just kind of give you a feel for how the high-level control scheme works, which is just sort of a heuristic thing that we thought up one morning, and not go into really any detail on the models that we put underneath and the control strategies that the actual theoretical control strategies that we use. So the basic idea then is that, as I've gotten at already, thermostatically controlled loads often operate in a discrete state. So typically just on or off. And we call the duty cycle, this is probably review for all of you, but the duty cycle is basically the fraction of the time that the thermostatically controlled device operates in the on state. So typically that's going to be 50% on the order of something like 50%. And then, so what we're doing now then is we're going to define a control mode, which is that we switch a fraction, and I'm going to call this gamma. A fraction of the loads, we switch them off on every time step. So we're operating in discrete time on the control, and once a minute, let's say, we're going to switch off some fraction of the loads. We'll call that gamma. And then we hold them off for a certain number of time steps, and that parameter in this model is m. So for example, with refrigeration, every minute we turn off, let's say just 5% of the loads in the population, and we hold them off for 5 minutes. And with refrigeration, it's important to make sure that you don't release them too quickly, depending on what the local control in the refrigerator is, because you can do something called short cycling of the compressor. But anyway, so the basic idea is that we continue cycling through, and I'm going to sort of show this in a schematic. But the key thing in terms of thinking about managing the end-use performance is that the combination of this parameter, how many we're turning off, and how long we turn them off for, is such that the loads still have plenty of time to meet their energy objective over the time scale of their duty cycle. So it might be that we're just going to operate the switch in the middle right here and turn the load off for 5 minutes, and that just means that it's going to operate a little bit longer later on. But we don't make that shutting off of the load so big that they can't maintain their set point anymore. Okay, so this is a great little schematic that I wish I could claim credit for, but it's actually due to Sasha von Meyer, who is here and is both at Sonoma State and CIEE. And so I'm going to do this in the context of refrigeration, but it basically, keep in mind that we can apply this to any thermostatically controlled discrete on-off state device. So imagine you've got a population of devices, we're going to call it size n, and some of them are on, these are the darker refrigerators, some of them are off, and on average, generally due to load diversity, the demand that they present to the grid is roughly constant, because they're cycling on and off at random times relative to each other. So then we send a signal to the devices that are off, to some fraction of the population. So gamma is our fraction, we multiply by n, go to the nearest integer, and then we turn that fraction of the population off. Okay, so they're off, and they're off externally. They're not off due to their local controller. They're off due to centralized external control. Let's see, let me make sure that I'm saying. And then, yeah, we say that they're going to be off for some number of time steps following that. In the illustration, it's just going to be one time step. So they'll turn on again in the next time step. So on the next time step, we send the same signal to another subset of the population. These guys now, they're allowed to come back on. But it might be that a couple more come on than had been on before, because in the m time steps that you held them off, if it's refrigeration, they've warmed up enough that they actually would like to be on. So an assumption that we're making here is that the local control is going to return to its original state. After you cut power, when you put it back on, the local control will do what it was doing before. And that's certainly true for mechanical thermostats, like a bimetallic strip. We're still trying to dig into the details on sort of new digital controls for refrigerators to see if that would remain true. And then, as you can probably see, like on the next time step, we choose another subset of the population, turn them off. These guys come back on. We just sort of cycle through. Okay, so then what happens, and this is maybe, hopefully your intuition will work with this, but basically what happens in equilibrium, we get to a point where we're forcing a certain subset of the population off, but we're making sure that everybody has enough time to meet their end-use energy goals. And so what that implies is that these ones have to be operating more than they were in the absence of control. So in average, in aggregate, everything is consuming what it was before you did the control. But you've got basically this group that you've forced off. Okay, so let's see. What else do I want to say? Yeah, so aggregate power is the same as it was before. It's roughly as smooth as it was without control. And this is really important. It's due to heterogeneity. We've got refrigerators with different compressors, different amounts of food in them. We've got people opening and closing their doors more and less often, and that causes them to sort of move through their cycle at different rates than they would. So they're all a little bit different. So that means that our aggregate power is sort of up and roughly as constant as it was before we did the control. Okay, so now we've basically got everything sort of under control, and we've got a parameter, gamma, that we can change. This is like our one little control input that we can change into the in the population. So we can basically think of the population as being in equilibrium subject to this gamma control. And now we're going to start moving gamma around to disturb the system from that equilibrium. So then rather than just sending off this fraction here, what if we turn off these guys as well? So of course, increasing gamma, that's going to decrease aggregate power. That makes sense. Note that it's just a transient change. Depending on how many you're turning off, if they can still meet their energy constraints and you have heterogeneity in the population, aggregate power is going to roughly go back to where it was before in the long run. But we're just looking at trying to get transient changes. But the interesting thing is if you decrease gamma, then basically the system, when it was in equilibrium with this gamma control, was expecting you to turn off some fraction of the population, but you didn't do it. And so you actually get an increase in power as a result. So this is sort of the key of how we're getting an increase in aggregate demand from the population, but only by turning devices off. Okay, so as I said, now we have one single control input to the aggregate system. Switching off more than usual, intuitively, that transiently reduces demand. Switching off less, this is the interesting thing, transiently increases demand. And then provided that gamma is small on average, the average demand should be unchanged. So now we can go through and we can start thinking about, well, how do we model this system in aggregate? What kind of control strategies do we apply to gamma? And that's detail that I'm not going to go into today. But we're looking at a bunch of different ways of doing it. PID works remarkably well. Minimum variance control, I'm going to show you some results for that in just a second. We're still working on getting the aggregate population model to work well enough for MPC. But the reason that this is interesting is because if you have some trajectory of a signal you would like to follow, let's say you've got a 5-minute dispatch signal and you want to follow that, and you have some idea of what your population is going to do over that 5-minute interval, you can start thinking about doing a receding horizon control problem. And so I think that there's probably some benefit to be gained by doing this, provided we can get a good model of what's going on. Okay, so before I go and show you some of the results, just to sort of motivate the kinds of loads that we're thinking about working with. So this is actually from about a 10-year-old study that Jonathan Kumi did up at Lawrence Berkeley Lab, where they looked at how much energy do different end-use categories on the grid consume. And what we saw when we were looking through all of these different end uses was the things that really stood out for potential for this kind of control was commercial refrigeration, residential refrigeration, commercial hot water, and residential hot water. So together, their coincident peak demand is, from this 10-year-old study, something on the order of what you might want to manage for renewables forecast error. Of course, we don't know if we can tap into all of this. But if we could, then it's simply problem solved. So I'm sure it's not that simple, but it at least says that these are exciting loads to be looking at applying this kind of a strategy to. And then the other thing that we've spent a fair bit of time, especially Taylor Keep and Froy Cifuentes have done some really great work here in terms of developing very detailed end-use models of refrigeration and water heating. So multiple state models, rather than just thinking about what's the bulk temperature in a refrigerator, it's important to consider the distribution of temperatures in the refrigerator. In the case of a tank water heater, we've actually got a stratified tank water storage model, because stratified temperature, because ultimately, it's easy to imagine with a water heater, all you care about is what's the temperature at the top where you're pulling hot water out. So it could be that the gradient, the temperature gradient could be really steep, but you don't care because you're still getting hot water out. So of course, as you draw water, if it gets cold, then that's a sort of failure of the end use, the way that we categorize things. But anyway, suffice it to say that it's been really important for us to get these details right in order to actually evaluate how effective is the control. And that's basically what I'm saying here. Okay, so then we put together a simple target trajectory where the idea is that we had some sort of baseline, what we thought demand would be in the model over some period of time. And then basically, because we're assuming this is forecast error, we're just going to say this is some normally distributed random noise around the baseline. And so we basically just add, every 5 minutes, we have a different random number to add to that baseline. And then we looked at different ways of sort of moving through those random numbers. Maybe it looks just like the 5-minute energy markets look like, where it looks like you've got these sort of step functions. Maybe it's what generation actually does, which is move more continuously. Anyway, then so this figure, we need to work on getting a slightly better one here. But this is basically the result where we're looking at refrigeration, where control starts right about here. And you can see that before, the blue line is what was actually the aggregate power demand from this refrigerator population. You can see that when we initiate control, we get pretty good tracking of this random signal, which is sort of scrunched up in here. The easiest way to look at the results is really here. So now we've got on the y-axis the error as a fraction of the load that we're managing. And so this starts to get interesting. So now we're just thinking about residential water heaters in the state of California alone. And what's on the x-axis is gigawatts of capacity in terms of the amplitude of this signal. Okay, so we're saying that we can get a signal that is 2 gigawatts in amplitude at this point using just the refrigerators, the residential refrigerators in the state of California, using this kind of an approach. And as we measure it here, at least the error looks relatively good. We have a lot of legwork to do in terms of comparing this to what actually happens on the supply side and what kinds of errors are acceptable. But at least this RMS looks pretty good. Another way of thinking about things, though, is what happens at the point of use. So now we're saying, well, what's the average temperature in these devices as we control them, as we move them around and shut them off for periods of time? So what we're looking at here is the deviation, the temperature deviation from what it would have been doing in the absence of the control. And you can see that we're looking at, on the order of a degree Celsius, is how much we might be moving in this case, the refrigerator freezer compartment away from where it would be in the absence of control. So maybe that's acceptable, maybe it's not. We're not really sure, but we know that our objective eventually is to try to get that as small as we can. And then another way, just thinking about, so what does this mean in terms of cost? So now we're looking on the y-axis at the annual value per device. This is actually not the result as strong as we were hoping for. But again, looking at the same axis, x-axis, gigawatts of amplitude, and then assuming certain values for what we call, in this case we're saying if this is regulation or automatic generation control, in the California Independent System Operator, they'll pay this sort of on the order of these amounts for getting that service. And so if we were providing that service using this approach, this would be sort of the annual value of one refrigerator to the system. So it's kind of a small number and probably not enough to support the installation of one of these load switches on its own. But if you look at things here, now we've got dollars per watt of responsive capacity. So this starts to get a little bit more interesting because, okay, so let's assume that it costs us, let's take this red line, $50 to install the load switch and to manage the program. Then this curve is telling us basically how much it costs us per watt of capacity to get how much it costs us to get that watt of capacity in a dollar per watt metric. And so what you can see now is that for these sort of values for the load switch, 50 to 25 bucks, you start getting stuff that's competitive with conventional generation. So that's sort of interesting. Big caveats here that we're still working on refining the control. Maybe we can't actually get this much capacity. Maybe we can get even more. It's still sort of open to improving our results. So, okay, so open questions and objectives and challenges. So we've got, as I said, work to do in terms of improving the performance of the controller. I think it'd be really interesting to think more about how we actually integrate this kind of a program into energy and ancillary services markets. It would be very interesting to understand what's the impact on system-level impact. So if we're replacing generation with demand response, what's the impact on emissions? We need to know more about what the impact of cycling these loads has on the actual, sort of long-term maintenance. And then this is, I think, a big issue. When we're talking about little loads that we're monitoring or that we're controlling and we don't have a lot to spend on communications infrastructure, how do you actually convince the California ISO that this is something that they should have paid for? How do you convince them that you provided a service that's useful to them? And I think that ultimately it's got to be some sort of a large sort of statistical sampling approach where, you trust that it's happening, but you do some sort of random sampling to verify that you're actually getting what you want. So I think with that, I'll close and take questions. Thanks.
Great. Thank you very much, Duncan. Okay, we'll have some questions.
Yeah, I've got a question. Wouldn't it be a lot simpler, I'm back here,
Oh, yeah.
to just do what Whirlpool said to me 5 years ago at their global headquarters, that if they replaced every refrigerator in California, they could save enough power to power up the rest of the country. Maybe that's changed to maybe half the country. My question is, how are the refrigeration people going to approach this? It could validate their warranties and the life of the operation of the units. And I question you don't have any industry data, and how come you haven't talked to Whirlpool in Evansville, Indiana, or GE in Louisville Appliance Park on some of this?
Right. Yeah. So we've actually initiated some conversations with GE. It's tough to get their attention, unfortunately, but as you might imagine. But it's not. We're not leaving this open. I think it's a really important question that we need to look at more. I think that the primary concern, as I understand things, is that we just want to make sure we don't want to short cycle these compressors if we're talking about refrigeration. So there are local controls in place to prevent that from happening, but we can also sort of structure the time that we keep these things off to prevent that from happening. Also, if you think about other types of end uses, I think water heating, there's basically nothing that you can do to break that thing in terms of the approach that we're taking. So maybe that indicates that ultimately we want to focus on water heating rather than refrigeration, which is why we're looking at both. Yeah.
If these load switches are external to the refrigerators, I believe what you're saying, then it means that the refrigerator light is going to be cycling on and off.
Right. No, this is.
And I would think that a lot of consumers would find that objectionable, so
Totally
you have to give them a good discount to
Right.
to
So
make them use
yeah,
it.
you either need a big discount or you need some sort of a little. Maybe there's a way to externally power the light. I don't know, but that we've worried about this one as well. And again, it points to water heating maybe as a better application. Yep.
Two quick questions. One is the $5 to $10 per megawatt hour for regulation.
Yeah.
I just don't believe it. I think the price for regulation in the real time, particularly during peak hours, is significantly higher than that.
It can certainly get higher, but this is like an annual average. And it's per megawatt. Yeah. It's not per unit of energy. This is just per unit of capacity that's right on the grid for an hour.
The other thing was with respect to having a large number of loads that are under AGC that are remotely wired. Have you looked at the California Department of Water Resources, et cetera? Because it's something like 20 or 25% of all of California's load is used to move water around the state.
Right.
And there's a lot of inertia in those systems as well. I'm just wondering if you.
So actually, pumping loads are already. They already have some control over these large pumping loads. So people have gone there. Yeah.
So you talk about integrating these flexible loads and things.
Mm-hmm.
How might you allocate the benefit in existing markets that these flexible loads provide to the ISO? I mean, would there be a simple way of distributing the cost of these ancillary services among each one of the residents?
Yeah, so I think that I sort of glossed this over. I think the most likely business model would be that you'd have some sort of an aggregator that goes and recruits loads. The aggregator interfaces with the California ISO, and then and basically gets all the revenue from there, and then they distribute that out to their loads. It's just like happens with demand response now, or not everywhere, but in a lot of demand response programs. That's how it works.
Do you think energy is just too cheap for demand response?
Well, let's see.
I mean,
what are you specifically? What's that?
If I had to pay, if you could save me $200 a month and my electricity bill was $1,000 a month, we'd talk.
Right. Yeah. Well, but I mean, then we're talking about energy efficiency, maybe more than demand response, if I understand your question. What I've been talking about today is specifically like we're not going to change how much energy these things consume. So basically, the bill to the consumer for the kilowatt hours should be roughly the same. Anyway, but I think energy is too cheap anyway.
You just mentioned the idea of an aggregator.
Yeah.
But we still are fighting the battle whether PG&E is going to make the signal that comes out of the smart meters available to third parties. So it seems like it's all being held in the politics.
Right. Yeah. And well, so PG&E could implement something like this. So there's one. If they really sort of dig their heels in, they could potentially do this. The other thing is that you don't have to go through AMI, right? And that's what all of the aggregators are being forced to do now anyway. But it would be great if we could make the AMI, access to the AMI data and control ability more open. I agree.
But wouldn't, I think that there is probably a lot of people may be resistant to the idea that somebody will control their devices and you'll have some permanent setup there on your refrigerator. Wouldn't it be a more plausible model to kind of have a separation where the demand response it goes all the way on one side of the meter in terms of, for example, having different priorities for different tranches of your fuse, and then it's up to the customer to decide at any particular point in time when their fuse is being reduced to half, whether they're going to watch the Super Bowl or whether they're going to disconnect the refrigerator.
Right.
So that it's not, you don't have that level of intrusion into the household.
Right. And so I didn't mean to dismiss that option, right? Like I think that all of these kinds of strategies can and should be on the table, but I think that that's the right approach if you're interested in sort of managing what's happening like in the hour ahead market, right? But if we're talking about really short time scale changes, even on the 5-minute market, I sort of question at least my desire to sort of look at what's the trajectory of prices that's going to happen over the next hour and figure out how am I going to distribute. It becomes like an optimal control problem, right? You have to figure out how am I going to distribute my energy use over that time period to minimize my costs. Like alternatively, if somebody pays me a bit so that they can be the one doing the control, and maybe I even get a bit of a reduction on my bill, I think it's possible at least that kind of an approach could work. But I think that it's a matter of time scale ultimately. I do think that if you want, if you're talking about sort of longer time scale price trajectories, that what you're talking about absolutely makes sense.
We'll take one
Duncan,
more question.
So you've done the analysis on the whole grid of this is the deficit versus what we could gain out of this distributed control analysis. But have you looked into how it'll affect things at the bus level when you start dropping loads?
Yeah, no, and that's an important point. I think that if you've got, you can start really messing around with the power flow. If you've got, ideally everything is sort of uniformly distributed everywhere, right? But if you've got sort of pockets of control, then you need to consider that. But you're already, the ISO is already doing that because they've got localized, centralized generation that they need to consider. So, but it is interesting to think about having moderately more distributed, or maybe even much more distributed response, and we haven't thought about that.
Okay,
Thanks.
Thank you very much, Duncan.